I'm Luis, and here I am with Tarek and Tanner from the .NET team. And we're here to talk to you about AI fundamentals in .NET. So this may be an image that you are used to seeing. And so first of all, I want to start off by saying thank you, random person who is doing this thankless work. But hopefully the part that it mostly illustrates as well is that it's very difficult for you to build applications and build solutions on top of shaky foundations, right? And so having a strong set of foundations is really important when you're building your applications. And so when it comes to the .NET team, there's a few areas that we've been focusing on here, right? And so primarily, the ones that we're going to be talking about today are tokenizers and tensors, right? So from a tokenizer's perspective, they're incredibly important and they're a foundational piece of building AI applications for a variety of reasons. If you're working with services like OpenAI, Azure AI Inference, GitHub Models, right? Tokenizers are very helpful in helping you manage context and manage cost in terms of understanding how many tokens are being sent with each of the prompts. And if we're working with local models, tokenizers are a pre-processing step that is used to turn text into tokens and vice versa. Right? When it comes to tensors, tensors are also a foundational piece of AI, right? And tensors are a way for you to encode, manipulate, and apply operations to multi-dimensional data. So they're incredibly fundamental when it comes to AI. Now, if you download the latest bits that are in .NET 9, you're going to notice that in the packages like Microsoft ML Tokenizers, which is the official package for tokenizers in the .NET ecosystem, there's a ton of new tokenizers that you have access to that are just built into the library, right? And so you can see a list of them here. When it comes to tensors and tensor primitives, you're going to notice that there's improvements in terms of the number of operations that are available to you to apply to these various data structures. There's also perf improvements that are there as well. And from a tensor perspective, it provides an exchange type that makes the efficient data manipulation and interop between various libraries within the .NET ecosystem that, again, are working with this multidimensional data. And so now, to tell you a little bit more about tokenizers, I'll hand it off to Tanner. Sorry, Tarek.
Yeah, thank you, Luis. Yeah, building a .NET AI application, which is interacting with language models, will require to have a tokenizer. The reason is language models don't manipulate directly the input text. Instead, it tries to convert it to a form of list of numbers, so it can be handled inside the language model. And the tokenizer is a component which is exactly doing that. So the tokenizer is just splitting the input text into smaller units, and we call this unit token. And the token can be like word, can be subword, can be a character or stuff like that. And after that, the tokenizer can map every token to some specific unique ID. And to do that, the tokenizers use something called vocab file. While you're creating a tokenizer object, you provide the vocab file, which is, this vocab file actually is containing all vocabs that the tokenizer can work with. Also, it provides a mapping from vocab to some unique IDs. For every vocab, it will have this mapping. So the tokenizers use this vocab file to do the mapping from the token to the IDs. So how we support tokenizers in the .NET? I mean, it's supported through a library is called Microsoft.ml.tokenizers. And this library is targeting .NET and Net Standard 2, which means it can be used in both in .NET and .NET Framework applications. Also, this library, we ship it as a NuGet package. So it exists in NuGet.org. This library also provides some abstractions, right? And the benefit of the abstractions is if you have like tokenizer abstract class, for example, and using this abstract interfaces, you can switch actually underneath the concrete tokenizer without changing the code if you are using the abstractions. Another benefit of the abstractions is it enables the interop between components. I mean, like one component can send a tokenizer object to another component and can use it through the abstraction interfaces without worrying about like what is the actual tokenizer is used there. We are supporting in this library, I mean, a list of tokenizers. We support BBE tokenizer, which is byte pair encoding, which is used with many models out there. We support tick token tokenizer, which is used with OpenAI models like GPT 3.5, 4, 4.0, and 0.1. We support Llama tokenizer, which is used with Meta Llama models. We support CodeGen tokenizer, which is used with code generation models. And we support other tokenizers like WordPiece and BERT tokenizers, which is used with BERT models. So let's jump now to see how we can use the tokenizer APIs. So first step here is, of course, I mean, like any new Git package, you need to reference this package. So if you see here, we are referencing Microsoft ML tokenizers. And I'm referencing here another package, which is the same. We call it data package, but this is specific for tick token because I'm using tick token tokenizer in my demo. But if you are not using tick token, so you don't have to reference this package. This data package actually includes vocab files that I talked about it. I mean, for tick token, so users don't have to worry about carrying the vocab files themselves or download it from somewhere. So first step, I mean, like we are referencing this. We are good to go now. Second step is to create the tokenizer object itself. And we have the pattern here to create any tokenizer. So you use the tokenizer name class, I mean, the like tick token tokenizer, and you call create method on it. This, for example, I mean, like we are using tick token tokenizer.create for model, and we're saying like, yeah, well, I need the tokenizer to work with GPT-4. If you want to create another tokenizer like Llama tokenizer, so you will do similar thing. You will call Llama tokenizer.create, and you go from there. So we are creating now the tokenizer object, and now we have the tokenizer object is ready. Second, we are going like operation, counting the tokens. So giving some input text, you want to count how many tokens can be generated from this text. This scenario is required, I mean, in a couple of cases, like if your application is using a service which is a language model service, which is charging per number of tokens that you are using. So you want to count the token before you calling the service to make sure that you are inside the allowed quota before calling. The second scenario is some language models restrict any request up to some max number of tokens. So if you are passing long text and is passing this max, so the result can be truncated and you get surprised with that. So counting tokens is kind of important scenario if you are running into these cases. So here in the code, I mean, I'm using the input text. It's simple sentence saying hello, comma, space, world, exclamation mark. And then I'm calling tokenizer count tokens, passing the input, and it returns the number of tokens that it gets generated from this input. I'm listing here also some overload, which is taking a span of characters. So this is showing like our APIs can be called with strings and also can be called with spans. So if I run this, it tells me like this input text can return 4 tokens. So 4 tokens can be generated from this input. Next scenario here is, actually, this is the most important one, which is this what it generates the IDs, the numbers that it can be fed to the language models. We have APIs called encode to IDs. It takes the input and it returns the encoded IDs that match this input. If you remember that we counted the token before, it's 4 tokens. So if I run this, I expect to get 4 IDs. So if you see here, I mean, we got like 4 IDs, 9906, 11, 19, 17, and 0. I'm showing here also another overload that you can control about, like if you want to encode up to some max token, you can do that. I mean, so we have overloads that it can take the max token count, and you can specify it, and it can encode up to this number. If you want to generate the full information of the tokens, means that the string tokens and the IDs for this token and the offset that map inside the input text, you can call encode to tokens. And this API will return list of encoded tokens. And this list will be, every encoded token will have the information about like the string value of the token, the ID, and the offset. So if I run this, it will give me, as we know that, it should be 4 tokens. And first token, the value of it is hello string, and the ID and the offset inside the input string, and so on for the rest. The other operation you can do using the tokenizer is, if you don't need to generate tokens at all, but you want to know that where is in the input text you can generate up to max count. So we have this API, the method is called getIndexByTokenCount, which can count up to some maximum and stop there, and it will return you the index inside the input text where it stopped. So you can know exactly, like, you know, up to here, it's matching this max token count. And we provide also, if you want to do this from the end, I mean, so you can count from the end up to some place, some index inside the input text. So if you run this, we will get about, like, if we are passing max token 2, so it's saying that up to hello, comma, this is matching 2 tokens. And if I'm searching from the end with 2 tokens also, it tells me like space world exclamation mark. This is where, I mean, like 2 tokens from the end. Last operation here, which is also important, is the reverse operation of the encoding. So encoding is encoding the text into IDs. So decoding is the reverse operation, which is convert the IDs back to strings. So if I run this, I'm passing the IDs, which is we generated up there. And this gives us back the same strings that we started in the beginning. So hello world. Yeah, by that, I will turn over to Tanner so he can talk about tensors.
Yeah, so to talk a little bit about tensors, we first need to kind of talk about what a tensor is. So a tensor in the most general sense is an abstraction over shaped data. So it's a general abstraction for describing and operating on any shape of data. And some of the other common terms you may hear about when working with tensors are things like scalars, which are individual values. For example, a single int or a single float would be a scalar value. Then you have vectors, which are effectively one-dimensional tensors. They are things like arrays or spans of data. So you're going to have many scalars within one vector. Then you have matrices, which are effectively vectors of vectors. They become two-dimensional pieces of data. And in some cases, such as math or even graphics programming, sometimes matrices will have higher dimensionality as well. But then you start getting into tensor being the general abstraction over all of those pieces of data. So a tensor could be a scalar or a vector or a matrix or even a piece of data that has more dimensions. And this general abstraction allows you to work with data mathematically and using a number of operations that makes it very convenient to talk about the structure of the data, to manipulate it and come to new answers and new results. Like Luis had mentioned, a lot of the stuff around tokenizers and tensors here are foundations of AI and ML. And even some of them are foundations of broader computer science. And one of the common operations you might want to do in computer science is something like you want to compute the sum of all values in a span or array of data. And if you wanted to do that, it's pretty easy to go and write it yourself. You track a result, and for every value that's in the input set, you just add it to that result, and you've computed your sum. This is great for simple scenarios, but when you start working with large data sets, especially such as in ML or AI scenarios, the amount of data you're going to be working on is going to change from 20 or 30 elements at a time to potentially thousands or millions of elements. You'll be potentially processing gigabytes of data in the worst cases. And so you're going to end up wanting to say, oh, this is a performance bottleneck. What can I do to improve the perf? And to improve the perf even a little bit, the code gets quite a bit more complex. You end up starting to have to consider things like loop unrolling, where within a single loop iteration, you're going to do multiple operations at the same time. Code gets a little bit more complex, but it's still not even close to as fast as we can get. And you've already tripled or quadrupled the number of lines of code you have to maintain. Beyond loop unrolling, you can start doing things like vectorization. This uses the hardware SIMD, or single instruction multiple data capabilities, to basically compress those unrolled operations back down into single operations. So this loop here, which is loading a vector's worth of data, in this case it's loading 4 elements at a time, is doing the same work as this loop here, but in one instruction instead of the 4 separate operations. And you still have to handle many of the same considerations, such as handling trailing elements that don't fit into the loop where you're handling factors of 4 at a time. You can also use larger data sizes that the hardware provides, such as vector 256 or even vector 512. And as you continue expanding the set of hardware you support, the number of lines of code you have to maintain increases. All of that, however, ends up paying off because, as you can see from the benchmark numbers here, for different input sizes, well, if you're only operating on 4 elements at a time, most of them are going to be fairly similar, taking somewhere between 1 and 3 nanoseconds worth of time. As you grow up, though, you'll see that the differences between the options continue increasing. So when you're operating on 65,000 elements of data, you're taking almost 30 times longer in some cases as with the naive loop as compared to what you could get with some of the more advanced options. But you don't want to have to do this for every piece of code you need to write, especially when you're writing very complex mathematical algorithms or handling more complex topics. And so the question is, what can .NET do to make that simpler for you? And the answer to that is we provide, starting in .NET 8, we started providing the foundation of tensor primitives. And in .NET 9, we've expanded that with more functionality. And so now you can get all of the power of the 300 or so lines of code that existed in the file before this that we browsed through in one line. And as Luis's slide mentioned, tensor primitives provides over 200 different mathematical functions, all vector accelerated and covering all of the math APIs that you've come to know and love that exist on both integers and floating point data types. So you have things like sine, cosine, tangent. You've got things like square roots, sums. You have products of data, so multiplying instead of adding all of the elements together. You have things like computing the hypotenuse of triangles, and you even get some of the more advanced functionalities that are more core to AI scenarios, like cosine similarity. And all of those functions are provided built in for you and accelerated for you, so you don't have to worry about that part. But tensor primitives itself is a foundational building block. It only operates on raw spans of data. It doesn't operate on the shapes of data. And that's why it has primitives in the name, because you pass it in the memory, and in some cases you can pass in the shape of the memory, but it doesn't actually give it to you in a friendly way. And so the next step on top of that is to provide a way to interact with the with the data in a more shaped structure. So you can actually define how the data looks. And to that end, we've started building, and in .NET 9 have shipped as experimental, Tensor of T. Tensor of T actually allows you to define spans over tensors, so you can have slices of the data, but also a regular tensor of T type that works much like system.array, but it allows you to actually specify the data. So by default here, this is basically just defining a read-only tensor span that defines the values as having a shape of one dimension. So it defaults to being exactly the same as a read-only span. But let's say that I wanted to operate on this so that it had, so that there were 4 columns with enough rows to fill in the rest of the data. To that end, we can define something like, we could say that it's a shape of 4 by 4. And so now this defines that it's going to take a slice of the data that represents a 4 by 4 matrix. Or we could define others so that it implicitly computes the number of rows for the data. And to this end, we're able to change how we operate on the data so that instead of doing things like summing all elements, it can instead sum all of the elements within a single row and do that repetitively throughout the data. So it allows you to operate in the data in a much more friendly and efficient manner. We definitely love for you to try out tensor primitives and tensor of T and provide feedback, especially for tensor of T since it's experimental. There's still a lot of polish to do there and still more performance optimizations even beyond what we've already got in there. So every bit of feedback helps and will help make it a better product when it is ready to ship for stable.
Awesome, thank you, that was great. Let me kind of switch over here real quick to a quick demo. We still have a few minutes here to kind of show you how all these pieces fit together, right? And so the scenario that we're looking at here is we want to perform semantic search over a collection of movies, right? So semantic search, meaning we don't have to necessarily look at keywords, but we're going to use a few of these components that we talked about here, as well as a few AI models to help us find relevant items. And so we're going to start off with the tokenizer. In this case, we're using the BERT tokenizer, and we downloaded the vocabulary file from Hugging Face, right? So it's available in the repo. The model itself that we're working with here is E5 small, which is an embedding generation model. To help us also do the embedding generation, we're going to use this MLNet Onyx embedding generator. Now, what is this generator? It's actually an implementation of the iEmbedding generator interface in Microsoft Extensions.ai, right? And so what we're going to provide to this embedding generator to construct it is a tokenizer, which is going to help us pre-process the text that we're putting in here. And we're going to provide a model path, which is going to be an Onyx model, okay? And what this embedding generator is going to do is it's going to pre-process the data. And pre-processing is effectively just, let me just go here real quick to the method. It's using that encode to IDs, right? So it's turning that text into token IDs, okay? Once we have that data, we are inferring. And inference here, we're using ml.net to run the tokens, pass them as input to the model. And we are using this apply Onyx model transform in ml.net to get the embedding outputs, okay? Now, on its own, the model itself does not give us the exact output that we need, so we need to do additional post-processing on top of that. And so we're applying some operations here, like mean pooling and normalize and divide. And if we look at what mean pooling and normalize and divide are doing, we're not going to get into the details of what those are, but there are some post-processing operations that help us get the actual embedding values here. And to help us do that, you're going to notice here that we're using a lot of the operations inside of the inside of Tensor T, right? Like unsqueezing, broadcasting, multiplying, right? And all of these operations are optimized, as Tanner showed us here, for working on this multi-dimensional data here, okay? Now, we have this other movie service, which is actually what we're going to use to sort of load our data as well as perform search. And to do that, we're using this in-memory vector store, which is actually an implementation of the Microsoft Extensions vector data set of abstractions that are there, right? And so what the movie service is doing is it's, in this case, it helps us load the data. And in this case, we just have a set of movie titles as well as movie descriptions here. And that's going to create an in-memory vector store for us. Once all of that is set up, we provide the generator, and when we say load async, this is going to generate embeddings for us and store them inside of this vector store. Once the embeddings are inside of this vector store, I want to perform a query for a family-friendly movie. Okay? Then I provide my search options, and then I call the search async method, which again, it's just going to perform a search. It's going to generate the embeddings for the query and find the most relevant items from that in that vector store and output those results. Now, if you take a look, for example, when I run this application, I say I want to find a family-friendly movie. The first hit that comes up here is Lion King, and even though it doesn't say anything about it being family-friendly, because we're using semantic search here, right, we're able to effectively return the actual result. And so this is a way or a scenario, right, where all these fundamentals really come together with the existing libraries that exist in the .NET ecosystem to help you build your AI applications. And so with that, I'm going to turn it over to the slides here. Make sure to get .NET 9. Make sure to try out system numerics tensors, try out ML tokenizers, give us feedback, and yeah, check out these resources to learn more.